Alright, so this is problem 34 from chapter 11, and the problem reads, in the Challenger Deep of the Marianas Trench, the depth of seawater is 10.9 kilometers from the surface, and the pressure is 1.6 times 10 to the 8th pascals, or 1.5 times 10 to the 3 atmospheres, ATMs. Part A asks, if a cubic meter of water is taken from the surface to this depth, what is the change in volume? And then it says normal atmospheric pressure is about 1 times 10 to the 5th pascals. And then it says, assume that K for salt water is the same as fresh water, given in table 11.2. Because it's really hard to show a page on a book, I have those values. So K for water, for our intents and purposes, according to the book, is 45.8 times 10 to the negative 11 pascals, or it can also be 46.4 times 10 to the negative 6 atmospheres. So it wants to know the change in volume if we take a cubic meter of water. So the volume is going to be equal to 1 meter cubed. And if we take it down to that depth in the Marianas Trench, what will be the change in volume? Because we know as the pressure increases, the volume will decrease and the density will change. So we need to use the bulk module, which is going to be, bulk module equation is B is equal to negative change in pressure over change in volume divided by the initial volume. So, but this is K, which isn't in this equation. We know that K is equal to 1 over bulk module. So we can rewrite this as the change in volume over the change in pressure times 1 over the initial volume. So the way that I solve it, just because personal preference, I like using atmospheres instead of pascals. So it also makes it easy because the pressure at sea level is 1 atmosphere. So I'm going to be using this one. So we know that K is going to be equal to the volume final minus the volume initial divided by the pressure final minus the pressure initial, and that's going to be times by 1 over the initial volume. So we know that volume is, the initial volume is going to be 1. We're looking for the change in volume. We have K over here. We know the pressure at sea level in atmospheres is going to be 1. And then the problem gives us the pressure at that depth in the Marianas Trench. So pressure final is equal to, where is it? 1.15 times 10 to the 3rd ATMs. I have to make sure I have the right pressure, because there's nothing worse than using pressure in pascals and pressure in atmospheres, because they're not the same. So we can then substitute, but first what we're going to do is let's isolate for our final volume. So if we times by the volume initial, gotta get rid of that. We have to times by the volume initial. And then all of that is also going to be times by pressure final minus pressure initial. And so that leaves us with the volume final minus the volume initial is going to be equal to K times the volume initial times pressure final minus pressure initial. And then we would just add this volume. So if we add this plus volume initial, those will cross off because they're equal, and then we've got to add that initial volume back over to this side. And so, just to save space, volume final is going to be equal to K times the volume initial times the change in pressure plus the initial volume. So, now if we substitute everything in, we're using atmosphere, so it's 46.4 times 10 to the negative 6th times 1, because it's 1 cubic meter, times the change in pressure, so 1.15 times 10 to the 3rd minus 1, because it's 1 atm at sea level, plus our initial volume again of 1. When you do that math, you get that don't have the negative sign, you get an increase in volume. It's a problem. So that comes out to 0.946 meters cubed as your final volume. So it went from 1 meter cubed and it got compressed down to a little less than 1 meter cubed. So that's our final volume once we've taken that volume of water down that depth. The question then wants us to find the change in density of the water once we've taken it down to that depth. And it says, so part B asks, what is the density of salt water at this depth? At the surface, salt water has a density that is equal to 1.03 times 10 to the 3rd kilograms per meter cubed. So, once again, well, we'll just do this down here. So for part B, we're trying to find the density. But in order to know the density, we need to know the mass. So we know that because density is going to be equal to the mass divided by the volume because of the units. So at sea level, we know that this is the density of salt water. We also know our volume. So we know that our mass is going to be equal to the density times the volume, which is then 1.03 times 10 to the 3rd times by 1, which is really nice. So we then know that we have to have 1.03 times 10 to the 3 kilograms of water in 1 cubic meter. So we can then find that the density is going to be, our final density is going to be our mass, because the mass is the same, we're not gaining or losing mass, times our divided by our volume finally. So we know that our mass is 1.03 times 10 to the third kilograms divided by our new volume, 0.956 meters cubed. And so that gives us our density at that depth, which is equal to, let me just double check this. So, times 10 to the third divided by 0.946. Yep, so that gives us a density of 1.089 times 10 to the third kilograms per meter cubed. And that's our density of water at that depth. So we found the change in velocity because we know as the pressure increases, the velocity has to decrease, or not the velocity, the volume has to decrease because water is slightly compressible. And then we know that because it's compressible, the density will change as its volume decreases, but the mass stays the same. And that's that problem.